So dear participants, let's start with another topic on first module of programmable logic controllers. Today we will discuss on input output signals and requisite processing. So for the input signals from various switches or sensors and output signals that are generated from the PLC for actuating the devices are concerned, we have already seen that they are of three types. They can be digital, they can be discrete, or they can be analog. The discrete signal remains either on or off. The digital signal, they produce train of digital pulses, and analog signal is the signal that is changing with the size of the change in parameter. Okay, now you see, whatever the signals are there or whatever the output signals they have to be generated, the CPU must have input digital signals of particular size and that are from 0 volt to 5 volt. Again, the output from the CPU is digital, which is 0 to 5 volt. So whatever your signals are in the input side or whatever your signal requirement is there at the output side, CPU will be generating the signals or it will be accepting the signals within this range only. So therefore, you can easily understand that there is a certain necessity to condition the signals so that they are acceptable by the PLC. Because you can never say that the process input or the field inputs will be always in this particular domain, or whatever signals you generate from CPU, that will be able to drive some of the field output. Accordingly, signal shaping, converting and conditioning is required. We will look into all these aspects in this particular lecture. Now you see, there is an inbuilt facility to enable large range of inputs and outputs to be handled, which makes the PLCs so easy to use. Because you see, whenever we are talking of, maybe I am talking of an Arduino Uno board, which is very powerful a board that accepts signals, but there you need to shape the signal properly. Because if you know that your signal is somewhere lying in between 3 volt to 10 volt, you know that that signal cannot directly be connected to the Arduino or interface to the Arduino, because the Arduino will be damaged if a signal of more than 5 volt is given to some of its input. Now this is not the case of a PLC. PLCs are already built in such a manner that they can handle a wide range of input and output. Definitely that depends on the particular model of the PLC and specification that has been given by the manufacturer for that particular model. That you need to be ensured. मैं बार बार बोल रहा हूँ कि कोई भी इनपुट आउटपुट लगा के कोई भी पीएलसी में लगा देंगे तो आप पीएलसी को जला बैठेंगे. So you need to be very sure. Although PLCs are rigid, they are capable to handle, but you should know what is that actually. Because अंदर में जो CPU है वो सिर्फ एक ही वोल्टेज जानता है, 0 वोल्ट से 5 वोल्ट. That's it. Now in case of rack instruments, there are cards which can be plugged into the racks so that the input output characteristic of PLC can be changed to a very versatile limit. Whereas in a single box of PLC, the input and output units are incorporated by the manufacturer. So that is the basic advantage of a rack unit actually. If you wish to apply the same PLC for a different range of operation than the earlier one, and if your PLC is a compact PLC which does not allow that particular range which you want as an input, it is not going to accept it unless you make some signal conditioning circuit outside and then send the signal inside. But in case of a rack mounted PLC, you have got specific cards for that particular application that you can take. Suppose your CPU, the basic CPU built, and the particular digital input outputs which are available over there for that with the basic CPU card, they are accepting say 0 to 10 volt, but your operation is from maybe 0 to 24 volt. Then you can have an additional IO card, digital IO card added to that rack so that you can handle better signal. So that is better signal means you can handle a different range of signal. Suppose your PLC, whatever it is a rack type PLC and the initial unit accepts only digital input output. Now you need a particular signal to be get into the PLC, which is 4 to 20 milliampere current loop, then you need another add-on module which can accept 4 to 20 milliampere current at the input side. Likewise, now the sourcing and sinking concept I have already told to you. This again I have given here just for a sake of remembrance. That is, this is the input unit. You can see over there, that is the input unit. Here this is the input device in which the current is coming from the PLC. So this is a sourcing connection, and in this case you can see this is a sinking connection where from the source power source is connected to the device, and from the device the current is going into the PLC. So this is a sinking connection. So all these things we know already. Let us go further. Let us see that what are actual the inside figure. What are actual the inside figure? Now you see this is the basic input circuit for discrete and digital DC inputs. Discrete and digital DC input, how they are given to PLC. Now you see whatever there is in the block, this particular thing, this is the input terminal where to you actually connect your field device, and inside this what is happening actually you do not know. You can see that here is the terminal where you connect your field device, and here is the signal that is going to the CPU. In between the things whatever they are actually the signal accepting, signal conditioning, signal shaping, whatever you say, they are the processing unit. Okay, this is why it is called IO processing. This is part of the signal processing unit. Now you see here what is there actually. There is a protection diode, right? There is a protection diode. You can see there this resistor 1, resistance 2, this resistance 1 and resistance 2. That means that this is a voltage divider, so that if a bigger voltage comes, it will divide it. Actually what is happening, that why it is used, because you know that this particular thing, this CPU that accepts voltage up to this 5 volt. Now here you are applying 10 volt, so it is going to destroy it definitely. So how you can save it? You see here, this is actually a voltage divider. Why this voltage divider is required? Because you are applying whatever voltage is there from the field point to drive an opto-isolator. You can see this is a new terminology, opto-isolator. Here what happens actually, whenever some signal is there, that activates an LED. Whenever this LED is activated, that falls on a phototransistor. Whenever light falls on the base of the phototransistor starts conducting. So whenever it starts conducting, there is a change in the level of the signal that is fed to the CPU. Now you see that this LED and this phototransistor, whatever they are, it is not a very big unit. It is just like a small IC, which is of the size of say IC741, you already know. So in the shape of an IC741, shape and size of an IC741, just like that, you can have one opto-isolator. Now you see why it is named as opto-isolator. You can see the signal is sent in the form of light. So your input circuit and the CPU circuit, input circuit from the field point and the CPU circuit, you see actually they are not connected through by some electrical mean. They are connected by this optical mean. So even if there is some problem here, this section might get damaged, and you can just replace the opto-isolator because the LED might get damaged inside. You can replace this entire card, that is the inside card, you can replace, but your CPU, which is the most costly part of the PLC, that will be saved. Now you see that whenever this signal, whatever we are sending here, it can be from 0 to 10 volt, for example, say. So that is a higher voltage. Since it is a higher voltage, that voltage has to be divided. Therefore this voltage divider is there. Here there is an LED. This LED is actually connected to the output panel of the PLC or input panel of the PLC, so that, sorry, not output, I must say the input panel of the PLC, so that the user can see whether the input has been there or not. If the input is present, the LED will give a light signal. When the input is absent, there will be no signal. Now there is a protection diode. This protection diode ensures that there is no reverse signal. That means signal with reverse polarity is trying to enter this system. Because if the signal with a reverse polarity can come, then it may damage this diode definitely. That means this LED. Or if this LED is damaged and it is shorted somehow, then it will be damaging this part. If this part is damaged, then it is a very tough condition because your opto isolator and the entire card has to be replaced. So therefore this protection diode is there. If there is a reverse signal, this diode will be shorted and the signal will be going to ground, like that. So such type of processing is required at the input side, and definitely every time you need to know how you are actually going to save your CPU. How you are actually going to save your CPU, but not only saving the CPU serves your purpose. It is very important that whatever input card you are using, that should also be having enough safeguard to save itself also, because damage of any part will cost at the end user who is using the PLC. Now you see here, when we are having analog signals, that can be inputted to the PLC, and if input channel is able to convert the signal to a digital signal, then we use actually an analog to digital converter, because analog signal cannot be directly fed to the CPU. Analog signal cannot be directly fed to the CPU. The CPU only understands digital language. Therefore, you need to convert the signal to a digital signal using an analog to digital converter. Now you see, with a rack mounted system, you can have analog input card that to be inserted into the rack. If you have a rack mounted PLC, it is very easy, because analog input modules, analog input output modules, which are called AIO modules, they are available separately from any manufacturer for that particular PLC. Because if you are using an Allen Bradley PLC, you cannot add a Siemens unit. If you are using a Mitsubishi PLC, you cannot put an Allen Bradley add-on card. So whatever add-on card you are using, that must be of the same family and the same manufacturer. Otherwise, it is not possible to add any card. Okay. Now you see, in many cases, you are having separate analog channels at several analog inputs to be measured, but you have only one analog card. Then what is going to happen? You might think that every time I will be using a new analog card, so I will be buying 3 to 4 analog cards, but analog cards are costly. Therefore, the concept of multiplexing is used. Such type of cards are also available, multiplexing cards. So they are allowing you to go for 4 input, 8 input or 16 input. Okay, all these inputs are analog in nature definitely, because we are talking of analog cards. Now you see, this is the multiplexer, these are the inputs. Okay, there is a channel selection signal. Okay, so now you see, if there are 4 pins, that means 4 inputs from the fields, then how many channel selection lines we require? We require actually 2 channel signal lines, because if it is 0 0, then this channel will be selected. For 0 1, it will be this channel selected. For 1 0, this channel will be selected, and if both of them are high, 1 1, then this channel will be selected. Now when one channel is selected, the signal from that channel will be going into the output. Output means output of the multiplexer. This particular signal, what is available at the end of the multiplexer, this will be connected to the analog to digital converter, from which the signal will be fed to the CPU. I hope this much point is understood. Now you see that how much synchronization of time is required, because if this signal is continuously changing, then to what extent you are going to keep this particular channel latched over here. So that signal is going to the analog to digital converter. Many a times it happens that analog to digital converter is not that fast, at which this analog signal is changing. So accordingly you need to design here certain sort of buffer, latch, all these circuits. So it is not that just simple like this you say block diagrams, but for the sake of understanding I am representing the block diagrams to you. Now you see what is the function of an analog to digital converter, ADC. Although many of you are definitely very friendly with this particular terminology, A to ADC, but here I will just give an outlook of the idea. You can see here this is an analog to digital converter, and I am talking of an 8-bit analog to digital converter. Why this is 8-bit? Because whatever analog input is coming, it is generating a digital signal of 8 bits. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8 bits. So it is, since it is generating 8 bits of digital signature, that's why it is an analog to digital converter of 8 bits. Definitely there can be more bit size, and as the bit size is more, you are having more and more accurate measurement. There is no doubt in that. Now you see how these things take place. You see a single analog input signal. So here you actually fit the analog signal that gives rise to on-off output signals along the 8 separate wires. So whenever you put some signal in this analog input line, then there will be changes in these 8 output channels. Someone will be high, someone will be low, like that. That will be changing. Okay. The 8 signals then constitute the digital word corresponding to the analog input signal level. अभी देखो, what is word? 8 bit को एक word कहा जाता है. So whatever analog input you are giving, that analog input will generate a particular word. You see, whenever it is 0 volt, it is the output analog input is 0. Say it is 0. When it is 0, there is no signal. But when it is 1, when the analog input is 1, you can see the output is 0, 0, 0, 0, 0, 0, 0, 1. When it is 2, the output is 0, 0, 0, 0, 0, 0, 1, 0. So when it will be 3, now you can answer very easily. It will be 0, 0, 0, 0, 0, 0, 1, 1. That means you can understand very clearly that every analog signal has got a digital signature. Signature in the sense that it is that particular value for that analog input. So there will be a particular word, for every analog value. Now you see, if I have got an 8-bit converter, then how many values are possible? 2 to the power 8. 256 different digital values are possible, which is from 0000, 0000 to 1111, 1111. That is 0 to 255 in hex format. Now you see the digital output goes up in steps, and the analog voltages required to produce each digital output are termed quantization level. Quantization level समझना बहुत जरूरी है. You see, जब भी कोई एनालॉग सिग्नल आता है तो डिजिटल आउटपुट चेंज होता है, राइट? ऐसा समझना गलत है. समझना आपको क्या चाहिए कि कितनी एनालॉग सिग्नल आने के बाद, कितनी मात्रा के एनालॉग सिग्नल आने के बाद आपकी डिजिटल सिग्नल में एक बार चेंज होगा. हियर इट इज वेरी इजी. 0 के लिए 0, 1 के लिए 1, बट ऐसा नहीं होगा ना. जस्ट सी, अगर 0 के लिए 0 है और 1 के लिए 1 है, ऐसे परिस्थिति में क्या होगा? आपकी एनालॉग इनपुट 0 है, सपोज इट इज 0 वोल्ट, आउटपुट इज 0. Then it is 0.1 volt, there is no output. 0.2 volt, there is no output. 0.3, 0.4, 0.5, ऐसे करके कोई आउटपुट नहीं आया. Ultimately, when your analog input is 1 volt, then it is changed from 0.0000000 to 0.0000001. Now this is not going to suffice your purpose. So accordingly, the resolution of a analog to digital converter is defined. Now you see the digital output goes up in steps. यहाँ पे आप देख रहे हो analog signal continuous change होता है. You can easily think, because analog signals they change continuously like this, but a digital signal that actually changes in steps. You can see here the steps. Now you see analog voltage, this particular thing you must remember. Analog voltage, minimum analog voltage that is required to produce each digital output is called quantization level. That is called quantization level. Now you see that the analog voltage the analog voltage has to change by the difference in analog voltage between successive levels if the binary output is to change. इसका मतलब क्या हुआ कि समझो, suppose you have this is one analog value and this is another analog value. अब ये वैल्यू जब यहां से यहां तक चेंज हुआ, देयर इज नो चेंज इन द बाइनरी आउटपुट. दैट मीन्स आपके एडीसी के आउटपुट में कोई भी चेंज नहीं आया. यू गॉट माई पॉइंट? कोई भी चेंज नहीं आया. इसका मतलब क्या हुआ कि वो एडीसी ये चेंज पकड़ने में सक्षम नहीं है. दैट एडीसी इज इनकेपेबल ऑफ आइडेंटिफाइंग दिस स्मॉल चेंज. यहां से आता है एक टर्म जन्म लेता है जिसको हम बोलते हैं रेजोल्यूशन. रेजोल्यूशन इज द स्मॉलेस्ट चेंज इन एनालॉग वोल्टेज which will give rise to a change in 1 bit in the digital output. Now you see, रेजोल्यूशन जानने के बाद अभी आप देखो क्वांटाइजेशन लेवल और रेजोल्यूशन में क्या फर्क है. क्वांटाइजेशन लेवल क्या होता है? इट इज द एनालॉग वोल्टेजेस रिक्वायर्ड टू प्रोड्यूस ईच डिजिटल आउटपुट. मतलब दिस इज वन क्वांटाइजेशन लेवल, दिस इज अनदर क्वांटाइजेशन लेवल, लाइक दैट. ओके, सो कितनी एनालॉग वोल्टेज देने के बाद क्वांटाइजेशन लेवल क्या है कि एनालॉग वोल्टेज यहाँ पे मे बी 0.5 आने के बाद एक बार चेंज हो गया. दूसरा चेंज कहाँ पे आया? 1.5 में चेंज आया. तीसरा चेंज कहाँ पे आया? 2.5 में चेंज आया. सो 0.5, 1.5, 2.5, दीज आर द क्वांटाइजेशन लेवल्स. मतलब वहां पे क्वांटिफाई हो रहा है आपका सिग्नल इन डिजिटल टर्मिनोलॉजी. हाउएवर व्हाट इज रेजोल्यूशन? रेजोल्यूशन इज, देखो यहां से 0.5 था और 0.5 से लेके 1.5 उसको आना पड़ा. सो 0.5 से 1.5, 1 वोल्ट इज द रेजोल्यूशन. फिर 1.5 से लेके 2.5 तक आना पड़ा फिर से चेंज होने के लिए. सो अगेन 1 वोल्ट इज द रेजोल्यूशन. ओके, विथ एन 8-bit एडीसी. 8-bit एडीसी में इसको कैसे कैलकुलेट किया जाता है? यू सी, इफ द इनपुट सिग्नल वेरीज फ्रॉम 0 to 10 वोल्ट, अगर इनपुट सिग्नल आपका 0 to 10 वोल्ट है, then this resolution is measured in a very beautiful manner. You can see it is not very tough to remember. अगर आपका इनपुट रेंज 0 to 10 वोल्ट है, अब ये इनपुट रेंज कौन सा होता है? अगर आपने कोई एडीसी खरीदा, आईसी वहां पे देखना एक इंटीग्रेटेड सर्किट जो मिलता है ना एडीसी का, जैसे कि समझो आपका इंटरसेल 70 वाला सीरीज का कोई भी लिया आपने, राइट, 809 लिया आपने, 808 लिया आपने, 804 लिया आपने, तो वहां पे देयर इज ए पर्टिकुलर पिन कॉल्ड रेफरेंस पिन. तो रेफरेंस पिन में आपने अगर 10 वोल्ट दिया एंड हियर कितने बीट है आपके पास? यू हैव एक्चुअली 255 बिट्स बिकॉज 2 to the power 8 is equal to 256. 0 to 256 255 होता है. सो टोटल 255 होता है. तो यहां पे आपका वैल्यू आता है 0.04 वोल्ट. That means if your signal changes from 1.1 volt to 1.1 let us take different example, 1.0 volt to 1.01 volt. I hope I am understood. Your signal is earlier 1.0 volt. From there it has got an elevation to 1.1 volt. Now do you think that this is readable by your ADC? Definitely it is readable because your change is 0.1 and the minimum voltage that the particular ADC it can measure is 0.04 volt. It is the resolution. Now if your signal is 1 volt, say if your signal is 1 volt and your signal is changed to 1.01 volt, now your ADC will not be able to detect that change, right? So accordingly you have to decide that what is the minimum level that you have to measure. Accordingly, you while purchasing a PLC, you see that your analog card whether it is able to detect that change or not. If it is unable to detect that change, then there is no goodness of purchasing that particular analog card. So I will stop here and I will continue with next part in next lecture.